Hi everyone, my name is James Larish, and today I'll be talking about Hammurabi, a framework for pluggable, logic-based X.509 certificate validation policies. This talk was originally given at ACM CCS 2022. So today I'm going to be discussing a somewhat fun idea, why TLS certificate validation code should be written in Prolog. Just to start, let's review what certificate validation actually is. So, during a TLS handshake, the server sends its public key housed in a TLS certificate, which the client or browser uses to start a secure session. But before doing so, the browser must first validate the certificate. Crucially, it checks whether this leaf certificate is actually owned by example.com and not by an imposter. The browser doesn't yet trust the leaf, but it does trust a relatively static set of certificate authorities, each with their own root certificate. If one of these CAs verifies that the leaf is authentic, and then signs the leaf with its key, the browser can trust the leaf. However, root CAs do not sign leaf certificates directly. They delegate this responsibility to intermediate CA certificates by signing them, which in turn may sign the leaf certificate. To validate the leaf then, the browser performs a depth-first search over all available certificates, starting from the leaf, looking for a valid path through intermediates to any of its roots. A leaf is valid if at least one such path exists. The full criteria for certificate chain validity is prescribed by various RFCs, primarily 5.280, plus the CA Browser Forum, a group that maintains its own set of additional baseline requirements for web-based certificates. Many of the rules for validating certificates may seem obvious. For instance, the domain in the certificate received must match the domain the user is trying to visit. In practice, the details of such rules, including this one, can be quite subtle. For instance, there are actually multiple fields within the certificate that may contain domains. RFC 5.280 says clients can use the common name field, while the CAB requirements deprecate the common name in favor of the subject alternative names field. The subtlety of validation rules like this one means that even industrial-scale TLS clients like major browsers may produce different validation results, meaning valid or invalid, for the same certificate. But this does not mean these clients' validation procedures are incorrect. Now, some differences may indeed be caused by bugs due to mistakes or misinterpretation, but others are actually expected. Consider, for instance, that specifications give clients the freedom to implement things like revocation checking or not. Furthermore, clients often have valid reasons, like backwards compatibility, for making their own choices independent of the specifications. The important question then is not, is the client correct, but what rules is the client enforcing? Or more specifically, what policy does a client enforce? We call a certificate validation policy the high-level, implementation-independent, logical rules that a client enforces to validate certificates. For instance, that the lifetime of all certificates be less than 1 year. Critically, policy is independent from mechanism, which includes the implementation-dependent code for retrieving information that policies check, such as parsing the start and end dates out of the certificate to calculate the lifetime. Unfortunately, within all TLS clients today, both policy and mechanism are expressed in the same, often low-level language such as C or C++, and entangled, meaning there is no clear division between policy code and mechanism code. Not only does entanglement make it difficult to analyze the policy of a given client and compare the policies of different clients, but it also forces new clients like standard libraries to retread the same implementation path as old clients to varying degrees of correctness and completion. For reference, Python's standard HTTP library did not support certificate validation at all until 2014. To address these problems, we built Hammurabi, a framework that disentangles validation policy for mechanism. Mechanism is pulled out and standardized in a program we call the Hammurabi engine, which is TLS client agnostic. policy logic is pulled out into a separate high-level logic program. Hammurabi completely replaces the certificate validation code in existing TLS clients. When a client receives a certificate, it forwards it to the engine, which executes the desired policy and then returns the result. Let's now examine how Hammurabi works, starting with the engine. So the client sends the policy to execute the leaf certificate, potential intermediates, and some other parameters to the engine. The engine then performs a minimal depth-first search from the given leaf to its root certificates, fetching additional intermediates as needed. But rather than a single path like before, the engine finds all possible paths from leaf to root by checking only that the parent actually issued the child and that the issuer's signature on the child is cryptographically valid. The policy is responsible for the rest of path validation, as we'll see soon. The engine discards all certificates not in this tree, then obtains the revocation status, which may involve network calls, of each certificate. Both the client and the policy can instruct the engine to perform certain revocation checks, if any. Next, it converts all information derived from the tree, plus more information about the system, like the current time, into a set of logic program statements or facts. Finally, it executes the policy over the facts and returns the result. So we'll now examine the Hammurabi policies in detail. Hammurabi policies are Prolog programs. They are composed of many Prolog rules that operate over the facts produced by the engine. They have one required entry point rule, valid chain, whose sole operand is the leaf certificate. To execute this policy, the engine queries whether the valid chain relation holds for the given facts. If so, the certificate is valid. For instance, this valid chain relation holds if the current time is between the not before and not after fields of the leaf. There exists a parent certificate that signs and issued the leaf, and that parent is a valid non-leaf, which is a recursive relation that must terminate in a trusted root. Prolog is particularly well suited for certificate validation because it allows validation logic to be expressed declaratively, and Prolog engines are built to efficiently search for paths that satisfy rules. Hammurabi may be distributed as a system service, as described, or a standardized library, or with bespoke implementations. But all engines must be standardized to produce the same facts and execute policies in the same way. We built our prototype in Rust as a system service contacted via IPC, and we used the SWI Prolog interpreter to execute our policies. To evaluate our prototype, we converted almost all of the C++ certificate validation code in native Firefox and Chrome into Hammurabi policies of less than 700 lines of Prolog each. We compare our converted policies, called Hammurabi Firefox and Hammurabi Chrome respectively, against the native implementations by validating 10 million certificate chains from certificate transparency logs in both Hammurabi and the native browsers to see if our Prolog code produces the same results. We find that the Hammurabi and native implementations agree on the validity of all 10 million certificates. Unfortunately, these certificates provide incomplete coverage, since most are considered valid. To address this, we generated 100,000 synthetic certificates using the Frankensearch fuzzing technique. Now, Hammurabi Firefox and native Firefox agree on the validity of all such Frankensearches, but Hammurabi Chrome and native Chrome disagree on the validity of 4, caused by a parsing error in native Chrome. Performance is not a focus of the work, but broadly speaking, we found that the validation times of browsers and Prolog policies are in the same range, a few milliseconds. For more details on performance, I'll refer you to the paper. To demonstrate reusability, we modified both Firefox in 100 lines of code and the Go TLS library in 50 lines of code to contact the Hammurabi engine for certificate validation. We then plugged in Chrome's policy, making Firefox and Go validate certificates like Chrome would. The major win here is that building new clients no longer requires certificate validation expertise. they can simply connect to Hammurabi and plug in tried and tested validation policies like Chrome's or Firefox's. We also leverage logic programming to automatically compare Hammurabi policies, whose C++ implementations would be otherwise difficult to compare. Consider these contrived policies. A certificate is valid in Firefox if the common name of the leaf is food.example.com, and valid in Chrome if it is example.com. We construct a new Prolog rule, Firefox only, which holds when the leaf is valid in Firefox, but not in Chrome. /+ is the not operator in Prolog. We can then create a query for this rule. Assume for now that a leaf is composed of just one field, the common name. Prolog fills in the variable x for us if it can, telling us that certificates with food.example.com are valid in Firefox but not in Chrome. So this is a gross simplification of this technique called imputation. Constructing the real Firefox-only rule required massaging the signatures of many different rules and special logic for handling strings like domain names. We leave such details to the paper. We used imputation to highlight 9 real-world differences between the native browsers, which we verified out of band. For example, we found that wildcard certificates enabled for top-level domains like star.com are disallowed by the CAB requirements, but Firefox accepts certificates for star.co.uk because it only checks whether the number of labels to the right of the wildcard is greater than 1. Chrome, however, rejects such certificates because it actually checks the public suffix list for top-level domains. Another example, Chrome enforces a maximum lifetime of 398 days for certificates, while Firefox does not, despite their root store policy document claiming otherwise. And that's for leaf certificates. For all 9 differences found, please refer to the paper. In conclusion, I'd like to leave you with the following takeaways. Certificate validation policy and mechanism are entangled today. Hammurabi enables reusable Prolog policies atop a standardized mechanism engine. Validation policies expressed in Prolog are comparable to existing implementations in correctness. And finally, expressing policies as logic programs means policies can be automatically compared via imputation. We have open sourced all of our code, including both Prolog, Firefox, and Chrome policies. Thank you.